Hello and welcome back to math class. The intersection of a line with a plane and the intersection of two lines, and it's all taking place in 3 space. Lines can interact with planes in 3 ways. They could pierce the plane and have one point of intersection. They could lie on or lie within the plane, so there would be infinitely many points of intersection. Or they could run parallel to the plane, just very much like an airplane flying across a flat area of ground and never touch it. So they could run parallel to the plane and there would be 0 points of intersection. So those are the 3 ways that they could intersect. Lines and planes. Here's an example. Find the points of intersection of a line with a plane. Now the line is in 3 space, so there's a vector equation of it. And the plane is in 3 space, and we've got the Cartesian equation of it. Solution method. Turn the line into its parametric equations. So here x will be 5 plus 2t, and so on. Y will be negative 5 minus 5t, and z will be 2 plus 3t. Now take these parametric equations and plug them into the plane. So it will be 9x plus 13y minus 2z equals 29, where x, y, and z come from the parametric equations of the line. So we're plugging the line into the plane. Look what we have here. It's a single linear equation in one variable. So that's simple math. Do it out carefully. And it turns out that t is a number. It's the number -1. Okay, so when t turns out to be a number, a single number, we conclude the following. There is one point of intersection. This line is piercing through this plane, and it meets it at a single point of intersection 3, 0, 1, which comes from taking -1 and plugging it into the parametric equations. 5 minus 2 is this 3. -5, subtract 5 times -1, which is -5, plus 5 is 0, and 2 minus 3 is -1. Again, let's do it again. Find the points of intersection of the line and the plane. Same method, get those parametric equations and plug them into the plane. Same thing will happen. We'll get a linear equation with just one variable. The math is simple. Multiply it out and collect like terms and solve. But in this case, we got 0t equals 31. Now this is never true, no matter what t is. So we can conclude the following. There is no t such that 0t equals 31. So the algebra tells us that there is no point of intersection. The line runs parallel to, but distinct from, the plane. And this is what that would look like. The algebra is telling you about the situation. One more time. Find the point of intersection of a line with a plane. A line and a plane. Solution, turn it into its parametric equations. X equals -2 plus 3t, y equals 4 plus t, z equals 1 minus t. Plug them into the plane, single equation, linear equation, one variable. The math is simple. Multiply it out, collect like terms. We have this. And again, the algebra is sending us a coded message. It's telling us that this is true for all t. It's always true no matter what t is. 0t always equals 0. And here's our conclusion. Any point on the line is a solution, and so the line must lie within the plane. Example, use a dot product to determine if a given line, intersects a plane. So the question is, does this line intersect this plane? Well, of course, we could do what we just did, find the parametric equations and plug it into the plane and multiply it out, collect like terms and solve and see what we get. But we want to use the dot product, see how it could be used. Let's use that tool from our toolbox. Solution. Well, first, a line is parallel to a plane if and only if it is perpendicular to the normal of the plane. So picture a flagpole sticking out of, rising up from a flat area of ground. And there's a line in this three-space scenario. The line is parallel to that plane if it is perpendicular to the flagpole, which is the normal of the plane. So what we'll do is examine the dot product of the line direction with the normal direction, which is the flagpole, and see if they dot to 0. Because if they do, then it's perpendicular to that flagpole and must therefore be parallel to the plane. So we'll dot them. Direction of the line, normal of the plane, see if it's perpendicular. And we got 8, so it's not perpendicular, so we can conclude this. Just another use of the tools in our toolbox. The line is not perpendicular to the normal of the plane because the dot product is not 0. The line is not perpendicular to the normal of the plane because the dot product is not 0. Therefore, the line is not parallel to the plane and must intersect that plane at one point. Moving along. Use the dot product again. Use the dot product to determine if the line intersects the plane. Again, examine the dot product of the linear direction and the planar normal. Well, here's the linear direction, and the planar normal is 4x minus 2z plus 0y. Let's do this in the proper order. 4x plus 0y minus 2z minus 11 equals 0. So the normal here is 4, 0, minus 2. And we'll dot that with the direction of the line and see what we get. We get minus 8 plus 0 plus 8, which is 0. Okay. The line is perpendicular to the normal and so is parallel to the plane. It remains to determine if the line is coincident or distinct from that plane. In other words, does it lie within the plane or is it parallel to the plane but distinct from it? So we'll test a point from the line and see if it's on the plane or not. So this point 1, 0, 1 is from the line. Let's plug it into the plane and see if it satisfies. There's our plane. We're going to test that point. Left side equals 4 times 1 minus 2 times 1. The left side is 2. The right side is 11. And so we've concluded, therefore, the left side doesn't equal the right side. And the point is the point, and therefore the line is not on the plane. Therefore, the line and the plane are parallel, but separate, distinct from each other, and never meet. Continuing. Okay, we've talked about lines and planes. How about lines and lines in 3-space and their intersections? Two lines can be related to each other in 4 possible ways. Now remember, a line and a plane interact in 3 possible ways. They either pierce, or the line is within the plane, or the line is parallel to but distinct from the plane. Here we have 2 lines, and they can relate to each other in 4 possible ways. They can be parallel and coincident. In other words, they can be the same line. They can be parallel but not coincident, and so they'll never meet, and there will be no solutions. They can have different directions and meet and intersect and have one solution, or they could have different directions and never meet. And if that happens, they're called skew lines. And an example of skew lines in real life would be when one highway meets another highway and there's an overpass. So they're meeting, but they're not really intersecting because they're meeting at a different level. So in the top 2, we have the same direction. So if they have the same direction, there's either no solutions or infinitely many solutions, And if they have different directions, there's either one solution or no solutions. So we'll be interested in the direction of these lines. Let's do an example. Example, find the points of intersection of a couple of lines in 3-space. Because the direction vectors of these lines are not scalar multiples of each other, we can see this at a glance. This is 1 times 2, but this is not 5 times 2. This would have to be a 10. And so they're not multiples of each other. So we're either in case 3 or 4 from here. They have different directions, so they either meet at a point or they miss each other entirely, and they're skew lines. Method to determine which. Look at their parametric equations, solve 2 equations and 2 unknowns, and see if they generate the same third coordinate. So that's what we'll do. There's our lines. Switch to parametric form. So line 1 in parametric form. Line 2 in parametric form. X equals 3 plus t, and so on. And so we'll take 2 equations and 2 unknowns. If they do meet at a point, then these x's would be equal to each other, and we could say that 7 plus 2s equals 3 plus t. And we could say that 2 plus s equals 9 plus 5t. Because they're meeting, they've got the same x coordinate, the same y coordinate. We've got these 2 equations and 2 unknowns. Now I'll omit the solution for how do you solve 2 equations and 2 unknowns, and we just arrive at this. S equals minus 3, t equals minus 2, according to this. And now we'll see if they generate the same third coordinate. Line 1 would generate minus 6 minus 3 times minus 3, which is plus 9. So minus 6 plus 9 is 3. While line 2 would generate, and that would also be 3. They both yield the same z coordinate, which is 3. And so they meet at this point. 1 minus 1, 3. Where did this 1 come from? It came from taking s equals minus 3, plugging it in here. 7 minus 6 is 1. Where did the minus 1 come from? It came from taking t equals minus 2, plugging it in here, and going 9 minus 10 is minus 1. Or we could have plugged s equals minus 3 right here. 2 minus 3 is minus 1. And the 3, again, we can use either parameter into either z and get the same number, which is 3. Finding the point of intersection of 2 lines. Let's do it again. Switch to parametric form. Pick 2 of them and equate. How about the x and y coordinates? Solve 2 equations and 2 unknowns. Remember how to do that and actually do it. I've done it here on paper. S is 1 and t is 2. Let's see if they generate the same third coordinate. Now if I plug in a 1 here for s, I get minus 2 plus 3 is 1. And if I plug a t equals 2 in here for z, I have 1 minus 2, which is not 1. It's minus 1. And we conclude the lines do not intersect. Yet they have different directions. So the lines are skew lines.